Hello. Motors. Where would we be without motors? Well, we wouldn't be flying any quadcopters, that's for sure. In this video, we're going to take a look at the basics of motors. We're going to look at brush motors and brushless motors and how they differ, and the interaction between magnets and electromagnets and all that kind of stuff. And this is another of those videos that you don't need to watch in order to build a quadcopter. It's just useful background information. Anyway, let's get to it. So let's just cover some of the basics of magnets. Magnets have a north and a south pole, and the opposites of these poles will attract. And I've put a little piece of tape on this magnet here. It's actually a bunch of magnets that I've stuck together. They're quite strong, these ones. You can see I was able to move it through the desk. And I've put a piece of black tape on the north end of this magnet. And here's the other one I had. And we'll see that the north and the south will quite strongly attract, and the north and the north will quite strongly, in this case, repel. And I can actually touch these together if I try really hard, but it's a bit of a waste of time to try and do that on video. And you may have also seen diagrams like this which draw these lines of force visually like this. So you can see it sort of goes out one end of the magnet and in through the other, and it's just sort of the direction is the arrows are a little bit arbitrary. I think there's not really going from one direction to another. Nothing's really traveling, but it's quite often drawn as going from north to south like this. And you can see down the middle of the magnet, the lines are all going through this material. So this is the strongest place of magnetic field. We can't actually put anything inside the magnet, so the strongest useful place is right on the end of it here, where the lines are very close together. And you may have also seen demonstrations like this where you put a bunch of little iron filings on a piece of paper with a magnet underneath, and they'll line up with each other like this so that you can visually see these lines of force. I don't have any iron filings to do that demonstration with, but we can do a similar kind of demonstration using a compass. So at the moment the compass is pointing to magnetic north, which is in that direction, and as soon as I bring a magnet in the vicinity, you'll see it changes quite wildly. Oh, they're attracting each other. Hold on. So it's changed this one quite a lot, and as I move the compass around, you'll see that it's going around and it's changing orientation like this. Seems to be sticking a little bit. Anyway, I think you get the idea. When it comes to making electrical motors, another important property of magnetism that we can make use of is the fact that materials that are attracted to magnets, such as this iron bolt here, as well as being attracted to magnets like this, they also influence the magnetic field as well. For example, this bolt on its own has no magnetic field around it. So when I try and do something with this little screw here, nothing's going to happen. And the magnet on its own, at that distance, approximately the distance of the screw, also does nothing to it. But when I connect them together, now I can pick up the screw because the magnetic field has been influenced by the fact that this material is magnetically permeable, so it sort of allows the magnetism to travel. Travel is not really the right word, but it influences those lines of force to allow us to shape the magnetic field in a certain way. And you'll see when I drop this, when I disconnect this, it should drop off like that. Now it just so happens that electricity and magnetism are linked, and this is probably one of the most important discoveries of our time. I'll put a link in the description to a documentary that I saw one time about Michael Faraday and how he had to try and convince his peers about invisible force fields surrounding wires that actually turned out to be true, but they thought he was a bit crazy at the time. But anyway, the way it works is you have a wire, and let's say we have electrical charge flowing through this wire in that direction. It sets up a magnetic field where the lines of force are sort of in a circle around the wire in this direction. So you could imagine it like this magnet being here and here and here, and sort of going around like this in a circle. But the lines of force, or the magnetism induced by this wire, is nowhere near as strong as this magnet, so I can't really demonstrate this for you, unfortunately. It'd be very difficult to get that much current through this wire to try and make it do something that we can look at. But by coiling a wire up, we can increase the strength of the magnetism. So what I'm going to do here is I'm going to put these two little circles on, and they're going the same way. So like I said before, say the magnetic field's going around like that. Interesting thing happens when we take this wire and we make a loop out of it, and then we look at what happens with the lines of magnetic force on each side of the loop. So if I turn this up like that, hopefully we can see that. Oh, this is a bit trickier than I thought with the lights. But in the middle of this loop, the lines of force are heading in the same direction. So they're both going, in this case they're going that way. So what this means for us is when we're trying to make magnetism from electricity, is that we need a smaller current to make a larger magnetic field, or we don't need as much current to make a magnetic field. So we can just loop wires around and around and around like this until we get enough of them that the magnetic field is strong enough for our purposes with the kind of current that we can push through this wire. And it also means that the shape of the magnetic field is going to be a little bit more convenient for us when we're trying to construct things with it, because it's going to be sort of in a cylinder, sort of a tube kind of a shape like we just saw here. So it's going to be shaped like this magnetic field instead of being that sort of awkward one that goes around in a circle like that, which is kind of hard to manage when you're trying to build things with it. So I have a couple of other diagrams that we can look at which might help to illustrate this as well. So there's a coil with lots of loops, and we're starting to look at something very much like that bar magnet that we have. And the magnetic field will increase with every loop that's added to this coil. So as a demonstration of that, I've wound quite a bit of copper wire around that bolt. This is not just any copper wire. You can't see it, but it has a very thin covering of enamel on it, so that the electricity can't just jump between layers of wire here. So if there was no enamel, the electricity would come in here, and it would just take the shortest path and go straight out here, and it wouldn't even bother going down the coil. So you need to have enamel wire or some kind of insulated wire if you want to try this, and that will make sure that the current comes in here and it goes round and round and round and round and round, and round a couple hundred times or so, and then it comes out. So that's how this is going to work. And I've got that little screw from here before, and as we saw before, this is not actually, oh, is it? Oh, I think it's just rolling. Wait a minute. No? Okay. Anyway, so I've got the little screw, and we're going to try and attract that to this end of the bolt. This will be the strongest end. And as I mentioned before, having the bolt in the middle of the core of the coil helps to increase the strength of the magnetic field as well, because the iron in this bolt will take on some of the properties of that magnetic field, and it will help us out. So I'm just going to connect this on here very briefly. I don't want to hold this on here for too long, because you can see that it sort of jumps. But what I'm doing here is essentially making a short circuit for a moment. And when we have a short circuit, that means there's not really any resistance in the circuit, so that we're going to have lots and lots of current going through this wire. And lots of current means that something's going to get hot somewhere, because there's no outlet for it. We don't have any resistors to dissipate that heat in a safe way. So that's why I'm not just going to hold this wire on for good. I'm just going to tap it on here quickly, just so that we can see this jumping. Oops, didn't do much, did it? There we go. Anyway, so that's how an electromagnet works. And the nice thing about electromagnets, as opposed to permanent magnets like these ones, is that the electromagnets, by changing the polarity of the current, we can actually change the polarity of the magnet as well too. So actually, let's see if I can do something with this one. The trouble with this is I can't get it too close, because it's just going to attract itself already like that. So let's see how close I can get it before it does that. About here maybe. Oh, damn it. Right, so let's see if this is going to attract or repel that. So it's north is the direction that we're facing. So it repels north, and it should attract south. Yeah. Anyway, so by changing the polarity, we can make a permanent magnet either push itself away or pull itself closer. So that's the point. So now that we know how to make a magnet from electricity, and we know that we can change the direction of the electricity to either push or pull a permanent magnet, suppose that we had two permanent magnets in this arrangement, so that's south-north, south-north, so it's sort of north is going that way, and we had in the middle a magnet that we could switch the directions of, so that'll be our electromagnet. If we made our electromagnet so that it was also south-north like this, it would line up and everything would stay the same. It wouldn't want to move anywhere. But if we switch the direction of the electricity, then we'd have north, south, and it would try and flip itself around like that. And if we could get it to flip itself around and then change the direction of the electricity again so it would flip itself again, and keep that going so that every time it tried to line itself up by flipping over, it would have the electricity switched so that it would just keep flipping and flipping forever, well, while we have the electricity running at least, we would come up with something like this, which I have constructed from a bit of wood and another coil, and we have another piece of iron in the middle to help create a nice strong magnetic field at this point. And the terminals of this coil are going over to this little patch of copper, and there's one on that side and there's one directly on the other side as well. And I can put this in the middle of these two magnets, and if I do it carefully, let's say I touch the negative of my wire to here and the positive of my wire to here on each side like that. Well, supposing that's going to give us the flipping relation, it would flip it over like that, and then I'd have my terminals of my battery the other way around. So as soon as it got to this point, it would try and flip over again, and it would just keep flipping and flipping and flipping. So let's have a look at that. To demonstrate that, I've set up this arrangement here. This thing is a propeller balancer. So it has these discs here which are very, very low friction, and it's when you put a shaft on here, it will allow the shaft to rotate very freely. And in the middle I have a couple of magnets, kind of the same thing as the magnets I had before, but they're all sort of glued into place here so they can't move, and they're on either side of where this shaft is going to go, like this. So when I put that down there, we'll see that the shaft is quite free to move. It will stop after a while, and when it stops, it's always going to stop level because it has these two magnets on either side, and they're always pulling. They're going to hold it level like that. So as I mentioned before, we have a little patch of copper on either side here. So I'm just going to bring my positive and negative terminals of my battery. I'm just going to hold these on here, and we should see the piece in the middle flip over and over like that. So what's happening there is quite fast, but every time it flips over, it's going to reverse the direction of the current. So it never gets to a state where it's going to settle down and stay still. It always just keeps moving and moving. And oops, did you notice that what happened just then? It rotated the opposite direction. So this motor, I'm calling it a motor now because that's what it is. It's giving us some motion, but it's not very useful because we don't know which way it's going to go. It might go that way, it might go that way. All we know is it's going to go one way or the other, and it's going to keep going. So that's one problem with this motor and why we don't see motors like this in use very often. The only thing a motor like this might be useful for is in a cell phone where you have a vibrator, a tiny little motor in your cell phone that goes mee, mee when the phone rings and stuff. For a motor like that, we don't care which way it goes, I think. So you might be able to use this kind of a motor for something like that. But generally, when we turn the power on, we want the motor to go in a specific direction. So this is not going to do that for us. But let's give it another try. Yep. There we go. Ooh, that's going great. Now, can you see Can you see any sparks there on the black terminal? Just here where I'm shaking it a bit. It's a little bit hard to see, but there are sparks. And at that point there, the electrical flow is being stopped and started. Every time it switches around, the flow is going to stop, and then it's going to start again. And that's actually creating little sparks there. And the point where these things contact, because they are sort of brushing, oh, it went the other way that time. Because they're brushing against the surface of this pad, this is called a brushed motor. So these little bits here we call brushes. And one of the drawbacks of this type of motor is that those sparks, after a while, they tend to make a bit of a mess on these pads. So you can see I haven't actually run this very much. And it's already starting to build up some messy blackness where those sparks are being contacting and stopping again every time. Let's have a look at a brushed motor that is a little bit more practical. These little things are quite commonly found in electrical toys and the like. If you break something open, you might find one of these in there, and it works like that. But this one is reliable in the direction that it will turn. So if I was to switch these around, it would spin the opposite direction to what it just did then. If we take a look inside, we'll see quite a few similarities to that funny thing that I made. And on the left and the right there is a permanent magnet on each side, so that'll set up a magnetic field inside this area. And if we take the central part out, we'll see this is a bit different because it has 3 windings or 3 coils for the electromagnet part instead of just the 2 that I had. So the problem with my motor is that being symmetrical, when you power it up, it could go one way or the other, and we don't really know which. But this one, I think the way this works is it's going to power up. One of these coils is going to be north, the next one's going to be south, and I think the third one does nothing. And then they'll switch around, and because it's not symmetrical, it's always guaranteed to go in one direction, the way that you wanted it to. And if we have a look on the end here, we can see there are, of course, 3 pads on the shaft. So this is, on my one, this is where the copper pads were, just where my fingernail is there. And if I turn this around, keeping it in focus, we actually have 3 pads on the shaft. And those pads are going to be touching onto the brushes, which are just inside the base part of the motor there. And they're just little soft tabs of copper or something. Quite soft, and they just sort of lightly touch on those pads and brush against it as it spins around. So as you can see, one of the major advantages of a brushed motor is that they're very simple. They don't need any complicated electronic control circuits to make them run. All you need is the battery and the motor itself, and you have it off, as it is now, or you have it on. So it's either on or off. Oh, what if we want to make it go at about half speed? It turns out we do actually need to have some control circuitry if we want to make it go at anything other than full bore or completely off. And one way we can do that, it's a little bit hard to demonstrate, but I'll try. Let's say I want it to make it go at about half speed. I can turn it on and off very quickly. Oops. So it's hard for a human to do that, because what you need to do is turn it on and then off so that it's on half the time and off half the time. But you also need to do it really, really fast, like thousands of times per second. So that's where our complicated or smarter control circuitry comes in. And I've changed the program on this a little bit so that we have the light on there still, and it's running kind of the same way as before. I have this transistor that we looked at in one of the earlier videos, so it's taking the 5 volts low power smarter electronics from here, and it's using that signal to power the high power LED over there. The only thing that I've changed is that I have this dial in here that lets me adjust the brightness of the LED. Now what's happening here is it's exactly what I said I wanted to do with the motor. it's turning this LED on and off very, very quickly. And when it's at about half strength, it's turning it on half the time and off half the time. And when I turn it up to full, it's turning it on all the time. And so wherever you put it in that range, it's going to be turning it on and off, say maybe about on 25% of the time or so here. So let's have a look at what the signal looks like on an oscilloscope, so we can get a look. We need to look at how this voltage is being switched off and on to explain the next part. I was just getting the oscilloscope ready, and I thought maybe I should explain why it is that we even need to use this expensive oscilloscope in the first place, because what I'm about to do is measure voltage on one of these pins here, the pin that's switching the LED off and on, the signal side of it. So this is the 5-volt side on the Arduino. So 0 volts or ground is off, 5 volts is on. So why can't I just do that with my voltmeter here, because I was using this to measure voltage just before and it was fine. But what we're trying to do here, actually we can measure something useful. So if I put the voltmeter on this pin, we'll see that it's 1 volt. So 1 out of 5 is about 20%. So that means that the LED is being switched on about 20% of the time. So it's useful in that we can measure that, but it's too slow to react, and we don't get a good picture of how that voltage is really changing over time. So the oscilloscope will give us a visual view, as I'll show you in a second, and it also lets us capture things that are changing very, very quickly. So here's the oscilloscope screen. In the vertical scale we have voltage, and you can see at the moment it's set to 2 volts per division. So each one of these squares is 2 volts going vertically, and the time is set to 500 microseconds per square. So horizontally each one of these squares is 500 microseconds. And LED is off at the moment, and we can see that it's at 0 volts. So this point here is 0 volts. It's at ground all the time. Now as I turn the dial, we'll see that you can see in the reflection of the screen the LED, the brightness of the LED, hopefully. And you can see that the voltage is being switched on and off. When I put it about here, it's on half the time and off half the time. So this is the halfway point. And we could use this to turn that motor off and on very quickly and get a smooth speed instead of a rough speed like I was doing with my clumsy human hands. And you can see that it is in fact in this case turning off and on at a frequency of almost 1,000 hertz, so almost 1,000 times per second it's switching off and on. And when I turn it all the way up, this pulse just kind of disappears and it's just on at 5 volts all the way. So it's 5 volts because it's so 2, 4, and then half of a square, so that's 5 volts there. And this is what we call pulse width modulation. And obviously pulse is a pulse like a heartbeat when you check your wrist to see if you're alive. That's a pulse beating. It's just going up and down, off and on. And the width of this is being changed, so that's why we call it pulse width modulation. Modulation is just a fancy word that means changing something. So this is pulse width modulation, and I wanted to demonstrate this because the term pulse width modulation comes up quite a bit, and we always call it PWM. We abbreviate it like that. There are different types of PWM. This one is called duty cycle PWM because the information that's conveyed in this pulse is basically just one number. In this case, it's kind of like a percentage. What percentage of the time is this thing on, and what percentage of the time is it off? I'll put a link to the Wikipedia page about this so you can read a little bit more about it, but I think we've pretty much looked at it all. But there are other types of PWM, and they will interpret the width of these pulses in different ways. So, for example, the width of this pulse right now is about, if I put it right here, it's 500 microseconds. So it's on for 500 microseconds, and it's off for 500 microseconds. And for duty cycle, we don't care about the length of the pulse. We only care about what percentage of the time it's high and what percentage of the time it's low. But for other types of PWM, we're going to be measuring the time between when the pulse goes high and when it goes low. And we can interpret that data in different ways to carry more information across this wire. But we'll get to that later on. So just to finish off this demo, I guess we should try with the motor as well. So now I have quite smooth control over the speed of the motor. Obviously, well, there's nothing to see, but hopefully you can hear the noise of the motor. So that's how brushed motors work. Their simplicity of control and the fact that you only need one transistor to control them, at least to control the speed in one direction. If you actually wanted to turn them the other way and backwards and forwards like that, for example, in a radio controlled car, you might want to go in reverse. So in that case, you do need a little bit more advanced controller than just a single transistor. But for something like this, where the motors are only going to spin in one direction, one transistor per motor is enough to do the job. And because they only require 2 permanent magnets, they can be made quite small and light. And the motors that are on this particular quadcopter are just little tiny ones like that, and they do the job for that case pretty well. But we're not actually going to be looking at brushed motors very much more in this series. Basically, this is the only quadcopter I have with brushed motors on them, because the brushless motors give us quite a bit more flexibility in control, and also they give us quite a bit more power and efficiency as well. The downside is that they are more complicated to control. So let's have a look at how a brushless electric motor works. This is one that I put together as a demo, and you can probably see just at a quick glance that it's already more complicated than the brushed motor. We've got 3 electromagnets instead of just the one, and a lot more than 2 permanent magnets. So this is the rotor. It's going to be spinning around like that, and it's on a nice smooth bearing so that it's not going to have much resistance. And we also have over here a speed controller. So this is the brain that's controlling these electromagnets, telling them when to turn off and on. And it's also, as well as just turning them off and on like we had before, it's actually reversing the polarity of the electric charge flowing through. So one moment it's going to be flowing through this way, then it's going to be flowing through that way. And it's managing the timing of all these switchings so that the north and south phases of these magnets, electromagnets, are turned on at just the right time to make these permanent magnets be pushed away or pulled towards them. And they're spaced at a certain spacing so that it's going to keep rotating in a certain direction when the magnets are turned on and off at the right speed. So it's quite a bit more complicated, and when I first started doing this video series, I thought I might try and make my own one of these, but it turns out it's actually pretty difficult, so I just gave up on that, and I used the same one that I had in the earlier thing that I was looking at. So this is just a speed controller that I use on the quadcopter, so I just chickened out. It's quite hard to make one of those, as it turns out. Much easier to make these coils and things, though, so I did do that part for the demo. Anyway, let's fire it up and see how it works. So it doesn't work very well. I have to give it a bit of a flick, and it doesn't work until you get it in just the right speed range. Here is the only range it will work. So unfortunately I can't grab this and turn it up and down too much, and I think that's just due to the way I've made it. It's not really I guess it's just not as precise as it should be, or this speed controller that's running it is not made for this type of motor. And I'll show you a brushless motor that we use on quadcopters in a minute, and you'll see that it's not just 3 electromagnets, it's actually 12 in most cases. But anyway, it's running, and there's no brushes, so it's called brushless. There's actually no physical contact between the rotating part and the static part. So one advantage of this is that you're not going to have the sparks, and that means that the brushes are not going to wear out over time, and you have more efficiency because you're not actually brushing a physical, there's no friction in the between the electromagnets and the permanent magnets. Now you may be thinking to yourself, wait a minute, in the brushed motor, the reason that it kept spinning around and around was because when it flipped over one way, the brushes would touch the opposite side of the pad, and it would reverse the polarity of the magnet. But there's no brushes here, and nothing's touching, so how does it know at what timing to switch these magnets here from north to south? Well, that's a very good question, And the answer is, one thing I didn't tell you before about electromagnets is that, so what we discovered was that passing an electric current through the coil would make a magnetic field here. And it turns out that the reverse is true as well. So if we pass a magnet across here, we can generate some current in these wires, and this is how electric power stations work. They, pass magnets around to generate current in wires. And I have this wire coil connected to my oscilloscope, so we can see the voltage that's generated between these 2 points here. And this is a very small voltage, otherwise I would have shown you with an LED or something, but you can see on the oscilloscope there, it's a little bit hard to show because it keeps sticking, but if I can move it around a little bit more reliably, there we go. So you can see on the screen there that this is generating some voltage ups and downs. So the way the brushless motor is working is, as these magnets whiz past, 2 of these electromagnets are going to be powered up. So one's going to be north, one's going to be south, and the third one is going to be listening, so to speak. So it's going to be doing this sensing thing that we were just seeing. And if I hold this up to the side of the motor now, see that when I get close to those magnets whizzing around, we see a voltage going up and down in quite a orderly fashion. It's up down in a sine wave. So the third electromagnet here that's not actually doing anything is looking at this sine wave, and it knows when a north magnet is coming past and when a south magnet is coming past. So that's how it can tell when to switch between powering up which of these 3 electromagnets. So to get all that to work, you do need quite a smart little brain over this side organizing things. By the way, in addition to switching the electromagnets off and on and listening for the position of the permanent magnets as they spin around, the ESC also has to manage the PWM, pulse width modulation, to make sure that the speed of the motor is what we want as well. So it really is doing quite a lot of work here, and it needs to have a fairly fast CPU to manage this, because as you can imagine, well, this motor is not very fast rotating, but in some of those really high RPM brushless motors that we have in our quadcopters, these magnets are getting spinning past here really, really fast, and this needs to be able to handle that. Anyway, let's have a look at an actual brushless motor and see if we can find some similarities between what I've made here. So I'll just lift this off, and this is just a piece of plywood with the magnets poked in there, and underneath I have actually a part of a brushless motor. No, I wasn't cheating, I was just using this as a thing to spin on like that, because it has a nice smooth bearing in it. But you can probably already tell what part of my motor this is analogous to. So this piece has the permanent magnets on the inside, and this one has 14, I think. Yep, should do. Mine has 16. I had to make it a little bit different, but basically this piece is the same as this one. So those nice strong magnets just sit around the outside, and we have a shaft in the middle, and propeller goes on the top, and this piece in the bottom is the same as these 3 electromagnets that I've put here, except that there are 12 of them, so we're not wasting any space in this one, that's for sure. So they are a little bit smaller, but they have a nicer core in the middle of them that helps direct this magnetic field straight outwards. So it's a pretty sophisticated little device, and as I said before, it's got some nice bearings in the middle. So I was just running that like that so that I could have a smooth movement, but it doesn't run like that, of course. It's going to be like this, so that those magnets are going to end up very, very close to the ends of the electromagnets, and you've got to be a little bit careful with these because they pull themselves in quite strongly when they get close. Just sort of, oh, I put a spacer on here, that's right. Get that out. Alright, let's try that again. Alright, so you've got to watch your fingers don't get jammed in there because that can hurt. But yeah, that's how it would sit on there. And then we just have the 3 wires coming out there. So it's a little bit more complicated to construct one of these, but there's actually no brain in here. It's not actually doing any thinking. All the thinking and the control is done by the ESC there. So let's have a little look at the sizes of this thing, because this is something that we're going to be talking about in future a little bit too. If I measure the outside diameter of the stator, or the piece that doesn't move, we should get 22 millimeters. And if we look at the vertical height of it, I can't really do it. Let's do it this way. About there. 5. Okay, it's supposed to be 5 millimeters. And that's what we saw on the outside just a minute ago, maybe if you noticed. So we have a 22, and then we have a 5, 2205. So these two numbers, it's one number, but they're sort of in 2 parts. It's like 22 is the 22 millimeters that we saw for the diameter of this piece, and then 5 is the height of the stator. So in this motor, this piece here is called the stator because it stays still, doesn't move, and this is the rotor because it's rotating, and the rotating part is on the outside of the motor as opposed to the inside, as we saw on the small motors that we looked at before. The motor on the outside piece was not moving, and just the shaft in the middle was rotating. But on this one, the whole thing on the outside is rotating like that. So this is known as an outrunner motor. So 2205 is the size of this one. And there was another number on here as well. 2300 kV. The kV number refers to how many revolutions per minute this motor will do if you power it with 1 volt. That's not to say it would run at 1 volt, because I think pretty sure these need more than that to actually start up and run. But if you were able to power it with 1 volt and you had no load on it, so you didn't have any propeller, it wasn't doing any work, it was just spinning, doing nothing, it would in theory run at approximately 2300 revolutions per minute. So if you were to run it at 10 volts, you'd get 23,000 revolutions per minute. So that's roughly what that number means. It's not really exact. It's just sort of a spec that they try to make the motor to work to. So a higher number here means the motor is going to spin faster, at least with no load on it, with no propeller. Yeah, it's a little bit tricky, this one. We might have to come back and talk about this a little bit more when we're talking about propellers or something. But for the mini quad size quadcopters that we'll be building in this series, we're typically going to be using about this 2300 kV motor. Let's just have a quick look at some other sizes of brushless motor before we finish up. So just hold these up and you can check out the specs here. So this is a 2208. It's the same diameter as the one we just looked at, but it'll be taller up and down like that. So it's 8 millimeters in this dimension. The X at the beginning in this case is just the model name of this. Sunny Sky tends to put X's at the beginning, and other brands put B's and C's or whatever. But the main thing that you need to keep in mind is this 2208 number. And this one is a 1100 kV motor in this case. So given the same voltage, it's going to spin quite a bit slower than the one that we were just looking at that was a 2300 kV. And typically a lower kV motor will be suited to larger props, and it's probably going to be larger as well because it's going to need more torque to spin the larger props, and it gets more torque by being larger in general. So larger diameter or a taller height will give the motor more torque. So moving on to one that's a bit smaller. This one is an 1804, so it's 18 millimeters across and then 4 millimeters up and down in this dimension, and it is a 2400 kV, so slightly faster than the one we were just looking at. but compare the diameters there, it is a little bit smaller. Over here we have a little guy. This one is a 1306 as soon as it focuses. And what is the kV on this one? 2300 kV, so it's the same as the one we looked at in the beginning, but it is only 13 millimeters diameter and 6 millimeters high, so it's pretty small. And the CW refers to clockwise, and that's telling you which way this nut is going to be tightened. So looking from the top, if I turn this clockwise, it will tighten the nut, and that can be useful. For example, over here we have one that is counterclockwise, I think, so CCW is counterclockwise, and that means that let's see, turning it clockwise should take it off, and turning it counterclockwise will tighten it. And it can be handy to have this kind of a thing, because the motors, as we looked at the beginning, two of the motors are going to be spinning this way, and two of them are going to be spinning the other way. And if you spin them the wrong way, the act of spinning the propeller can actually make these nuts come loose if they're not lock nuts, which they're not in this case. So sometimes we might want to have the thread of this motor nut going a specific direction to make sure that when the motor spins up, it's not going to like loosen itself and make the prop fall off. So that's why you can have clockwise and counterclockwise motor directions. These days people tend to be using lock nuts more, so if you have a lock nut like this with a little bit of nylock in there, you can tighten that up nice and tight, and it doesn't matter which way the thread is going, it's not going to fall off. So it's actually quite a bit easier to just have one of those. Anyway, so these two motors here are the ones that I'm going to be using in this particular build series. They are 2204, 2300 kV. The 22 diameter is quite a common thing because these nuts, the holes on the bottom here are made to a specific spacing, and you'll quite often find that when you buy a frame, it'll say it's made for this mounting size. So that's why the 22 is quite common. Anyway, that's that one. And on the other quad that I'm building, I'm going to be using this, which is a 2300 kV. Oh, it doesn't say. Sorry, I thought it was going to say on here. But this is a 2206. So it should be the same height as this other one, which was a 1306. But it's a lot, yeah, it looks about the same height. But it is, of course, a lot larger diameter. Anyway, I think that's going to do it for this video. We've covered a lot of what might have been a little bit boring theory about how motors work, but I think it's quite handy to know the details, and at least you'll know what people are talking about if they say things like this in the future. Anyway, thanks for watching, and I'll see you in the next one.